Down there, life continues. The traffic is awful, stocks go on trading, and Star Trek is still showing.
day, grade 8 learners. Welcome to today's Natural Sciences lesson. My name is Patuchezo Singo, and this lesson is proudly brought to you by the Harding Department of Education. In today's lesson, we are going to be learning under the knowledge area, energy and change. The topic is visible light, and the subtopic is radiation of light and spectrum of visible light. All right, now let's go through the lesson objectives. So these are the goals that we want to achieve at the end of the lesson. So at the end of the lesson, you should be able to explain that light is emitted from luminous objects, explain that light travels in straight lines, explain what happens when light is dispersed by a prism, explain how a rainbow is formed. All this is sourced from your CAPS document on page 50. Now let's move on. Pre-knowledge. So if we go back in time, remember in the 7th grade, we learned about the transfer of energy, in particular solar energy. So we did learn about the transfer of energy. So we are going to be building up on that foundation that we have learned. So now let's dive into the baseline activity. Number 1, what is the source of natural light on Earth? Question 1. Question 2, why is photosynthesis in plants important? Why is photosynthesis in plants important? Okay, so I'm going to give you 3 minutes to quickly do this activity, and then after 3 minutes we're going to do the solutions together. Don't forget to send in your solutions to our WhatsApp line, which is at the bottom of the screen. I'll read it out for you: 079 578 2908. So see you after 3 minutes. Welcome back, learners. Now let's answer these questions. What is the source of natural light on Earth? The source is The sun. It is, of course, the sun. Why is photosynthesis in plants important? Why is that process important? The process of photosynthesis is how plants make their food and supply oxygen to other living organisms, which makes the process very important. And the source of light for that process is, of course, the sun. It is, of course, the sun. Now, let's go on to terminology. So these are the terms that we are going to come across during this lesson and many, many other lessons to follow. So we need to learn their meanings or what they mean. So the first one is visible light, which is our umbrella topic, which is our topic for today. Visible light is electromagnetic radiation that can produce a visual sensation. Wavelength. This is the distance between one crest of a wave and the next corresponding crest. The next term is frequency. This is the number of waves that pass a certain point every second. And then spectrum. This is a band of colors produced by the separation of components of light by their different degrees of refraction. And then refraction is the bending of any wave when it passes from one medium to another different medium that has a different optical density. Now let's look at slide number 2 for our second set of terms. Radiation. This is the energy that is emitted by electromagnetic waves. Luminous means emitting light. Illuminated. This one is an object that provides light by reflecting light from another source. So we call it illuminated. And then to reflect is to throw back without absorbing. Now, let's talk radiation of light, which is the first half of our subtopic. Remember, our subtopic is radiation of light and visible spectrum of light. So we're starting off with radiation of light. Okay, so light can come from different sources. From our baseline activity, we've already established that the main source of light is the sun, but light can also come from other sources, and these different sources can be objects that give off their light, and we call these objects luminous because they are emitting light. So we have the sun as our main source of light, and there are other objects as well. You can be thinking of them now as I'm going on, that are also capable of emitting light. Objects that do not give off their light are called illuminated objects. So these are the objects that reflect the light that comes from other sources. So they're not giving off their light. They're just reflecting light that comes from other sources. Now, the light energy that comes from luminous objects is transferred by a process called radiation. And remember, when we're learning about solar energy in the 7th grade, we learned that light is a form of energy. And light is a form of energy known as electromagnetic radiation. Now, we know that the sun is the primary source of this radiation energy that we have on Earth, the energy that is the source, or rather is the driving force behind the process of photosynthesis and many other processes. Now, the primary source is the sun, but there are other objects that are also luminous. There are other objects that are also capable of emitting light. And such objects, or examples of these objects, are electric light bulbs and candles. We've got your electric light bulb, which is a source of light. It emits light. We've got candles, candlelight. We've also got fire. If you've got a fire going on outside, you can be able to see your surroundings because those flames do emit light, or that fire is emitting light. and making it able for you to see your surroundings. It is emitting light. So there are other sources of light besides the sun, but our main source is actually the sun. Now, the light energy from the sun, we said the sun is the main source of light energy, right? But then how does that light energy get to where we are? What path does it have to follow? Now, the light energy from the sun travels through space. It travels through space. And space is a vacuum, meaning there is nothing in space. It is a vacuum. Remember, light does not need particles to be transmitted. So it can simply travel from the sun where it is emitted all the way to Earth. And it travels extremely fast in a vacuum. Remember, light does not need particles for it to be transmitted. So in that vacuum, it travels at an extremely fast pace, at an extremely fast speed of 300,000 kilometers per second in a vacuum. So that is the speed of light in a vacuum. It is 300,000 kilometers per second. But where is the sun? The sun is 150 million kilometers from Earth, and it is a luminous object that radiates light into space. And that light travels at 300,000 kilometers per second to reach us. Okay. Now, we also have another object up in the sky, and it is called the moon. The moon is not a luminous object. The moon is an illuminated object. We are able to see the moon because it reflects the light of the sun. So the moon is an illuminated object, which drives the point. We can only see illuminated objects because light shines on them. So those objects that do not emit light, we see them because light shines on them. That is how we are able to see them. So I've got a picture here just to further emphasize on how far the sun is from us and how fast light from the sun reaches us. So between here, this is a vacuum. It is a vacuum. Okay, it is a vacuum. There's nothing there. There is absolutely nothing there between the sun and the earth. There is absolutely nothing there. So the light from the sun travels at a speed of 300,000 kilometers per second over a distance of 150 million kilometers. So how long do you think it takes for the light to reach the earth? That is your thought. Now, light energy is radiated from luminous objects. So when light is radiated from a source such as a light bulb or a torch, a beam of light can be seen as visible. Like if you're in total darkness and you're holding a torch and light is being radiated from that torch, you are able to see a beam of light. This tells us something. This tells us that light travels in straight lines. The beam is only visible when particles, maybe such as dust or water droplets, scatter the light. But what we know now, because of that beam, is light travels in straight lines. This is why car headlights show up well in the mist. They show up well in the mist. That mist, those water droplets that will be in the atmosphere will be scattering the light, and we are able to see the beam of light that comes from the headlights. Now, beams of light tend to diverge from their source, forming a cone shape. Think of a torch light, it forms a cone shape, or a light that is coming or beaming from a lighthouse. This phenomenon is easily seen with the car headlights, with the lighthouse, with spotlights on stage. and torch beams. The further the light travels, the less the beams tend to diverge. So if the light has to travel a long distance, then the less chances there are that the beams are going to diverge. Light that comes from distant objects is taken to be traveling in parallel rays. Parallel rays are those lines that never meet. Remember, parallel lines will never meet. However, if they are close, they will still be divergent. So here are stage lights or spotlights on stage, and you can see the beams of light radiating from the source. You can see the beams of light radiating from the source. Then you can see this cone shape from the lighthouse. This cone shape from the lighthouse, the shape of a cone, the shape of a cone. You can see it radiating from the lighthouse. Now, there is one way of proving that light does, one, travel in straight lines, two, also for us to be able to see illuminated objects, light has to shine on them. And we can do so through the use of a pinhole camera. A pinhole camera is a basic camera that shows how light behaves and how it travels in a straight line. A pinhole camera is used to form an upside down image of a luminous object on a screen. A pinhole camera is a simple optical device that forms an image without using a lens or a mirror, meaning you can actually make your own pinhole camera at home. So this is the basic structure of a pinhole camera. It's got a pinhole here, and then we have a box, and then at the end there is a screen where the upside down image is formed. So this is the object, and you can see it is upright, and then this is the image. It is shown as upside down on this side of the box, which we refer to as the screen. And then this is the pinhole. So how can we make our own pinhole? It can be constructed using simple things, for example, a milk box or a shoe box that has been painted black on the inside. So we need a container that can have 1, 2, 3, 4 sides to it, so that we have one side where you can have a screen, and then one side where you can have the hole that will let the light into the box, and then the box is painted black on the inside. Now, how is the viewing made on a pinhole camera? So the viewing hole is made with a pin, like you can make it with a pin at the other end. Right. And then the other side, so the opposite side, the side that is opposite the side where there's the pin hole that has been made, there a screen or tracing paper is fitted. This is where the image is going to form. So the light enters the tiny hole and forms an image on a screen or tracing paper at the back of the camera. So the hole is facing the back of the camera. The hole is facing the screen, and the hole is where the light goes in. So the amount of light that goes into our little pinhole camera is controlled by the size of the hole. You can make the hole smaller, or you can make the hole bigger. So it controls the amount of light that gets in. So here is another illustration of a pinhole camera. This is our object. And then light, it is an illuminated object because it reflects light from other sources. So our object is the tree. Then this tree reflects light, and the light travels in a straight line, goes through the pinhole, and hits the screen. So once it reaches the screen, this side as well, all the parts of the tree that reflect light are going to form an upside down image on the screen of the pinhole camera, Now, so when light passes through that small hole, this is what happens. An inverted image or an upside down image of the object will be viewed on the tracing paper. You can also use tissue paper if you do not have tracing paper. You can use tissue paper and you can also use tracing paper. The light rays also cross from the left to the right, so that the image is mirrored as well as inverted. So that's why the image appears upside down, because the light rays, they cross from the left to the right. That's how we have a mirror image that is inverted or that is upside down. So here is a pinhole camera and our object is a tree. What is our source of light here? Our source of light here is the sun, then we've got our tree, then we have our pinhole camera. We have our pinhole camera over here. So light from the sun is radiated onto the tree or the object, and then light passes through the pinhole camera, and then it crosses from left to right, and when it gets to the tracing paper or the screen, an inverted image is formed. So light travels in straight lines. Our pinhole camera proves to us that light does indeed travel in straight lines. So now we've reached our first activity for this lesson. I'll read out the questions for you and then give you time to answer them. Question 1. Give the meanings of the following terms. Luminous, A. B. Radiation. Question 2. From the pictures below, list the objects. A. You cannot see in the dark. B. You can see in the dark. Right, take 5 minutes to answer these questions, and then after 5 minutes, we will do the corrections together. Don't forget to send in any questions you may have to our WhatsApp line, which is 079 578 2908. See you after 5 minutes. Welcome back, learners. Let's answer these questions together. Give the meanings of the following terms. Luminance means emitting light, radiation, the energy that is emitted by electromagnetic waves. Now take a quick minute to quickly copy down these corrections. Now let's answer question number 2. From the pictures below, mark the objects you cannot see in the dark. Objects that require light to be emitted from a different source for you to be able to see them. So in the dark, you will not be able to see the table, and you will not be able to see the stack of books or the pile of books. Which of these objects can you see in the dark? You can see lit candles, you can see the fire, and you can definitely see light bulbs. Take a minute to copy down the corrections. Welcome back. Now let's move on to the second half of our lesson. We're going to be learning about the spectrum of visible light. So far, we've learned that the sun radiates white light. So what is white light? White light is a combination of 7 colors, which you can see clearly whenever there is a rainbow. And the collection of these colors that you're going to find that we see on the rainbow is called the spectrum of visible light. So all those 7 colors that make up the rainbow, that they actually make up white light. So white light is a collection or a combination rather of all the different colors that make up the rainbow. Another thing, light is called a wave. Why? Because it travels and moves in a repetitive pattern. But see the pattern that light creates. Remember, you can see me because of the light that is radiating on me, but you cannot see the light waves in, can you? We cannot see it. But light is called a wave because it travels, it moves in a regular, repetitive pattern. So it travels in waves. So here are the different waves. Here are some is an illustration of the different waves or the colors that when combined form white light. That when we combine them, we form white light. So each color of the visible spectrum is special in its own way. So we can differentiate them. So each color has a characteristic wave Some colors have long waves and others have short waves. So this is how we are able to differentiate the colors. So what is wavelength? Wavelength is the length of one wave pattern. What is one wave pattern, or what is wavelength? Wavelength is a distance between two consecutive crests. So this is a wave, this is a wave. So the difference between these two crests, consecutive means following each other one after another. Two consecutive crests, the distance between these two is the wavelength, as well as two consecutive troughs. And this is the distance between these two is also wavelength, and it is measured between 2 points that are in phase. It is measured between 2 points that are in phase. Now, wavelength, we've said, is measured from one crest to the next crest. Crests that are following each other, that are coming one after another, and from one trough to the next trough. Note that waves also have units, and very, very short waves are given this unit, or they are called according to this unit that is called nanometer, and the abbreviation is small letter n and small letter m. So very short waves are measured in nanometers. They are measured in nanometers. The shorter the wavelength, the shorter the wavelength, the higher its frequency, because it means that more waves will be able to pass a certain point at a given time with greater energy. So we say the short waves have very high frequency. The short waves have very high frequency. So here are some examples of different waves that we meet from time to time. And we've got radio waves, the ones that send your signals all the way to your radio. They have quite the long wavelength, but when you move towards the left, sorry, my right, which is your left, towards my right, the waves become shorter and shorter. I've got infrared radiation, the smaller waves, the visible light, X-rays, and then gamma rays. So they become shorter and shorter and shorter. And these that have a short wavelength, they are able to pass a certain point quickly, meaning they have a very high frequency, and this means they have greater energy. So there are 7 colors of the rainbow. Can you tell which colors of the rainbow they are? They are red, orange, yellow, green, blue, indigo, and violet. Orange, yellow, green, blue, indigo, and violet in the visible light spectrum. Each of these colors are different and special. Has its own frequency that is associated to it, and each has its own wavelength. That's why they can be differentiated. What is the name of the 7 colors of the visible light spectrum? Just memorize this acronym. Roy G. Biv. R for red, O for orange, Y for yellow, G for green, B for blue, I for indigo, and V for violet, and V for violet. Now, light has its own primary colors, and they are red, green, and blue. They are called the primary. Note, these are very different from the primary colors of paint. So, we said that white light is a combination of these 7 colors of the visible light spectrum. Red, orange, yellow, green, blue, indigo, and violet. And the primary colors are red, green, and blue. And the combination of the 3 primary colors will give us white. the combination of the three primary colors of light. When they are mixed, they will give us white. And then when we split white, we get the 7 colors of the visible light spectrum. We get the 7 colors of the visible light spectrum. Now, speaking of splitting light, let's learn about the dispersion of white light. Now, the speed of light, we spoke about when we're talking about the speed at which light travels in space, which is, do you remember, 300,000 kilometers per second. The speed of light changes, however, when light is moving through a different medium. We said in space, there's nothing, there's just a vacuum. So when light is traveling in that, its speed is 300,000 kilometers per second in a vacuum. So when light is traveling through a different medium, the speed changes. So the speed of light changes slightly depending on the medium through which it travels. It travels faster when it's traveling through space, and then slower when it's traveling through optically denser mediums such as glass. It slows down when it is traveling through denser mediums. It slows down. So let's say, for example, we have a glass and then white light strikes the side of that glass prism. So it was traveling in which medium before? It was traveling in air. And then when it strikes a glass prism, remember we're saying light can travel through glass. So when it strikes the glass prism, which means it's now traveling through a different medium, one which is optically denser. So what's going to happen? Let's find out. So a prism is a block that is made from either glass or perspex, and it is capable of splitting white light into the different colors of the visible spectrum, the 7, the Roy G. Biv. It is capable of splitting because it is in that denser medium. So this causes light rays to slow down. Light strikes the side of the glass prism. What's going to happen? It's going to slow down, bend, and called refraction, bending of light. So when it strikes that prism and starts traveling through a denser medium, it slows down and it bends. It slows down and it bends. All along the white light has been traveling in air. Now it's traveling through a denser medium. It's going to bend. So this is our white light. This is our white light traveling in which medium? A. And then reaches this medium, glass, slows down and bends. You see, once it has reached the glass prism, slow down, bended, this process of refraction, something happens. Let's continue. So the side of the prism is to the top, the roll it is angled. So the light is going to strike the side of the glass prism at an angle. And the color that we see after the light has bended depends on its wavelength and frequency. Remember the number of waves that pass a point at each second. So as it bends, remember white of all 7 colors of the visible light spectrum, and that have different and different frequencies. So when the white light bends, they split, or there is the dispersion of the white light. There's the dispersion of the white light and it splits into the 7 colors. So they bend according to their wavelength and their frequency. So they bend according to their wavelength and their frequency. Red and orange light has the longest wavelength and the lowest frequency because of the least amount of energy that they have. So they are refracted the least. They the least. Violet, indigo, and blue have the shortest wavelength and the highest frequency because of that higher amount of energy. So they bend the most. So there we go. There is our color violet wavelength. Some of the colors here: blue, there's the wavelength; green, there's the wavelength; yellow, 570 to 590 nanometers; orange, 590 to 629 nanometers; 620 to 750 nanometers. These are the colors, and you see the different light they bend at different angles. They are refracted at different. When the light is bending due to it's traveling at inside or traveling through a denser split, they bend at different angles. They have wavelengths, they have frequencies, and this spreads them out. This phenomenon of splitting is known as dispersion. It is known as dispersion. It is not always easy, however, to distinguish the colors of the spectrum. So next time you see a rainbow, please try and distinguish the visible spectrum. Try and see which one is orange, which is red, which one is yellow, which one is green, blue, indigo, and the diagram below shows a clear distinction between one color and the next. So, sunlight, prism, refraction happens, there's dispersion. Dispersion happens, they bend. So the one that bends the most is the one that is at the bottom. The one that bends the least is the one that is at the top. The one at the bottom bends the most. It has the shortest wavelength and the highest frequency. The one that bends the least naturally goes at the top. And there we go. So we've got red, orange, yellow, green, blue, indigo, and violet. So these are the 7 colors that make up our white light. Now, can you see them here? Let's try. Okay, here's our rainbow. I will start from this end. I can see red, there's a bit of orange, yellow, of course, green, yes, blue, yes, but it is quite difficult to distinguish between indigo and violet. Please do try from home. Look for pictures of the rainbow. If it's not raining currently, so do look for pictures of the rainbow and try and distinguish between the 7 colors that make up white light. More on dispersion. How does a rainbow form? So we know the 7 colors of the rainbow, but how does it form? So a rainbow will form after a storm, because after a storm, there are usually tiny water droplets that are left in the atmosphere. And these tiny little droplets of water act like a glass prism. What does a glass prism do? It disperses white light. So the water droplets disperse the light that is coming from the sun. So that's why you usually see a rainbow after a storm, and the sun is bound to be shining at that particular point. So the water droplets will disperse the light from the sun and reflect it towards the direction of the light. And this makes it very possible for us to see a rainbow if the sun is behind you. There is a picture of a rainbow. So that is how a rainbow is formed. Now, which brings us to our second activity. Number 1, explain how a rainbow is formed. Number 2, what is meant by the dispersion of light. Number 3, white light consists of a range of different frequencies and wavelengths. A, give an example from nature that shows how white light can be separated into different frequencies and wavelengths. Number 2, name the different colors that make up the spectrum of visible light. Take 5 minutes to do this activity, and after 5 minutes, we will do the solution together. Welcome back, learners. Let's go through the solution. Explain how a rainbow is formed. A rainbow forms when tiny drops of water remain in the atmosphere after it rains. The rain droplets act like a glass prism, and by so doing, they disperse light from the sun and reflect it towards the direction of the light. This makes it possible to see a rainbow only if it rains. What is meant by the dispersion of light? This is the splitting of a beam of white light into its seven colors when passed through a transparent medium such as a prism. Please do take 1 minute to copy down these solutions. Welcome back. Let's answer question 3. White light consists of a range of different frequencies. A. Give an example in nature that shows how white light can be separated into different frequencies. The key word here is in nature, and this is when a rainbow forms. It is all natural. Name the different colors that make up the spectrum of visible light. They are red, orange, yellow, green, blue, indigo, and violet. Please take a minute to copy down these corrections. Welcome back, learners. Now, let us wrap up our lesson. What did we learn today? Today, we learned that light is emitted by luminous objects, and light travels in straight lines. Light travels its fastest or at a very fast speed when it is in an empty space, such as a vacuum. Light is made up of a range of waves with different frequencies and different wavelengths. And the seven colors that make up white light are red, orange, yellow, green, blue, indigo, and violet. We also learned that violet has the shortest wavelength and the highest frequency, and red has the longest wavelength and the lowest frequency. We also learned that a rainbow forms when light falls on water droplets in the air. That's why you usually see a rainbow after it rains or after there's a storm and the sun is shining, especially if there's still water droplets in the atmosphere. You will be able to see the rainbow. Don't forget, grade 8 learners, to send any questions you may have concerning this lesson and any solutions to any of the activities that we did today to our WhatsApp line, which is 079-578-2908. Now, here is the homework activity. Take 3 minutes to quickly copy down each question, and then we'll continue after that. Welcome back, learners. Now, in our next lesson, we're going to be learning about opaque and transparent substances. All right, grade 8, thank you so much for joining me in this lesson. I hope to see you in the next one. Bye-bye.